Good morning and welcome to the 2021 Facebook Hacker Cup Round 3 and the solution video to problems D1, D2, and D3, Expl-ore-ation. So in this problem, you have a bunch of robots and they are exploring some ore mine for you. And they need to collect samples at optimally every single position in this cave, on this floor. Now the floor has varying terrain, and this is a bird's eye view of what it might look like. And unfortunately, you need to collect these samples like soon. However, the mine's flooding, and the water's going from height 0 to height 1 billion. It's going to be a big problem if you don't let these robots move to safety. So the robots, I mean, they can collect samples. It's okay if they get destroyed, but obviously once they're destroyed, they can't collect or transmit samples to you. So you want to make sure to collect the samples with the working robots, and optimally you want to collect as many samples as possible. After doing that, you want to use as few robots as possible. And the question is, how do you do that? So let's look at a quick example. It's a lot of information to try and put all here at once, but one possible thing that might happen is maybe over time things start flooding, and then I'll draw the flooded squares in blue. So maybe first we get this square gets flooded, and then maybe this square floods, and then in the next time step all of these ones flood, and then maybe at the next time step these squares all flood, and then maybe this square floods and this square floods, and then maybe we need to know, okay, what is the height of, or what is, let's get a sample here and get a sample here, and then maybe after that this floods here, this floods here, and then maybe we want to get this sample here, and those are the samples we're interested in. So the question is, how many robots do we need in order to get those samples? Well, we need one robot here, for sure. And this robot, when we need this sample, he's going to be kind of alone on his own little island here, because they can only move up, down, left, or right. So he's going to be trapped there. He'll be able to get the sample at the time we need it, and transmit it back to us, but that's gonna be all he's able to do for us. For this robot though, you may remember back when we were looking at this robot, or at this sample, the grid looked like this. So what this robot could do is we could drop a robot in, he could sit here, wait till the right time to collect the sample, and then he could move all the way over here, and then just chill out here. Then some more flooding happens, so maybe we flood this position here and this position here. And now the robot can move over to this square here. I think this was the one I picked earlier anyway. And then he can get this sample as well. So even though both of these eventually get separated by the time we're interested in this sample, a robot could pick this up, know that, okay, this is going to get flooded, so he's got to move across it really quickly, and then eventually pick up the sample as well. So this is where the tricky part of the problem comes from. How do we figure out how to reuse these robots in a smart way? And so we'll start talking about solutions here. Turns out a fantastic way of looking at this is going back in time. So instead of having things just disappear on us, instead, if we have land appear, if we imagine doing this in reverse time, we start with the water at a really high level and have it go down over time. This is a much simpler problem to solve, because now we know, well, when an island appears, it's just an island by itself, and eventually it might get connected, but the island becomes important when there's a question mark on it. So if we have just some island alone, I guess one thing I should mention first is that if we ever need to collect samples when the water will already be above that, then we can just ignore that space because it's impossible to get. So yeah, we'll ignore that. And this is a solution to D1 in particular. We'll talk about D2 and D3 in just a moment. So yeah, so the water, we're imagining the water as decreasing over time. When we have some island, it's fine to just ignore the island in the beginning. But then once we have some query on some island, and we'll process this query at the correct height for it. When we have this query, we're like, okay, we can now put a robot on this island. And we know the robot will always be safe now because the water is decreasing. So we know this is the last part of this island that this robot needs to be on. It's possible that there might be some other robot we also need. Maybe we need a robot over here. And then later on, these will become on the same island, so one of them will be redundant. But for now, like at the point that we need the second robot, these things are separate, which means we're going to need two robots to be in two separate places if we had the water rising, if we went forward in time. Okay, so that's the idea. Let's go into a bit more implementation detail here because that was a little hand wavy. Basically, what we can do is we can have one disjoint set node for every position on this grid. And when a position when it goes from water to land, we can union it with the ones above, down, left, and right if those things are also land. So yeah, we can process things like that. And then for each disjoint set node, we can mark whether or not this node is like used by a robot or not. So to do a quick example, maybe we'll go back in time. Initially, everything would be filled with water, but we'll say the first several moves just mark things as filled with land. So, okay, stuff is all filled with land. And now the next thing we do is we erase this, oh, maybe not. The next thing we do is we query this position. So this happens at whatever height we are. This is water height like 50. 50, we have this query. And then we answer it and we say, okay, so all of these things have been unioned together. We now can mark this entire component as there's a robot on this component. So now we lose some water. So this water disappears. And now we join this together with this component. So this is all now one component. And also with this component. So this whole thing on the left is all now one component. And now we join this together here. So we join this thing on the right with the thing on the left, or the thing on the left with this thing, and like we join these two and these two. So in total, we've merged all these two together. And now since these are all one component in the disjoint set, and the disjoint set knows that this component has a robot on it, we can say, well, the robot can come from either of these. Right? So earlier in time, the robot could be on either of these. Eventually, later in time, it's got to be on this right side because, well, we have queries on this right side. We don't have them on the left, so we need to handle the ones on the right. But earlier in time, the robot can handle all of this land. And then maybe after that, we get this water space back into land. So now the robot can be there. And then maybe we have a query here. But we don't have a robot here, so we have to create an additional robot for this part, and then we can continue doing this process. So that's kind of a rough sketch for the solution idea to problem D1. Now this works for D1, works quite well, and this is kind of a classic idea. But for problem D2, we're given the additional constraint that now we have to handle a change in what time we need each of these spaces to be relevant for. So before, each space just had only one time that we had to have a robot on it, which might have been impossible. But now we need, for each space, that time might change between queries. Now for D2 and D3, this is the same problem. The only difference is for D2, you need to, or for D3, you need to have a solution that works online. So in other words, the solution will work, and like you don't need to see what all of the queries are before being able to answer them. For problem D2, you're allowed to look at all of the queries. You know what all of the questions are in advance. You can come up with the answer to all of the questions in any order you want, and then you just have to sort your answers at the end so they match the order we asked you the questions in. So that's what makes C2 easier. Sorry, D2 easier than D3. I'll talk about one small approach to that here. All right, so the solution idea to D2 is the same general idea as the solution idea to D1, but we have to do a bit more bookkeeping. So in general, what we were doing for D1 is we had disjoint set nodes, and each disjoint set node worried only about what things it was connected to and whether or not there was a robot there. And we could say, yes, there is a robot here now, or we could say something like, join these things together. And if there was a robot in there for one, there will be for another. Now the problem with D2 is that we can't say there is a robot here now, because there might be for some queries, but not for others. And the way we can handle this is we can say each of these requirements that there's a robot there is true for a particular length of time, not in terms of time of water level, but in terms of time in the queries that you were asking. So maybe you have like Q1, Q2, Q3, Q4, and Q5. Some square might be active from, well, maybe from the beginning to Q3, right? And then at Q3 it gets changed, or at Q4 it gets changed, and then you have some other requirement here. Perhaps, maybe for some different square. Or maybe the height gets set to something that's impossible at Q4. And then maybe you have some other requirement that some other space is active from like maybe Q2 all the way to the end. Right? So you have these different requirements. Each requirement is active for a time of the queries, for a particular group of queries. And what we can do then is we can say, well, each disjoint set component will be required to have a robot for some group of the queries. Right? So we're still going to process this as like a sweep of the water draining, going from highest to lowest. But now each disjoint set component won't just store whether or not there's a robot in it. It'll store for all possible queries, store whether or not there's a robot in it. So like for query 2, so maybe like we have this event here. So we need to say, okay, from query 1 to query 3, this component contains a robot. And now maybe we have this side here. This says, okay, for query 2, maybe we'll say query 2 to query 4, this component on the left contains a robot. Then when we merge these together, there will be a robot in this new component from query 1 to query 4. And that's the idea. We need a way of storing these and merging them quickly. And this might be a little bit complicated because this might be very messy, right? So in this example, there's just one range for each of these. But it's possible that in one component, we might have something that looks like this. Maybe you have it in just query 1, and just in query 3, and just in query 5. And then in this other component, you have something like this. Right? So you need to merge these two together. We want the union of these two sets of ranges. Now, we can't iterate through everything in this bigger component, because we might add things one at a time to it, and if we have to look through each of them every time, this would be n squared. So what we can do is look through the group with fewer ranges of queries and merge that into the bigger group. That means each query, every time it's merged into another group, will be merged into a bigger group. So each of these ranges can only be merged log n times. This is the classic small to big trick. So each thing is only merged log n times. Each merge you can do with a tree set, with being a little careful with it, in just log n time. It might take longer than that, but if you do take longer than that, you'll remove one of these things. So you can amortize that into the cost of adding it to the tree set. It might also be removed once, and then you don't have to pay for that in your runtime. And then the runtime analysis works out well. So that's the idea of problem D2. It's basically the same as D1. You just have to be clever with coming up with a solution. Of course, for D2, it's the same as problem D3 if you're able to come up with a solution to D3. So if instead you understand this next solution, but not this one, then the solution to D3 will work as well. This is just D2 has maybe two possible main approaches that are intended at least. There might be other ones as well. And D3 just has the one that we know of anyway. OK, so what about D3? For D3, obviously this approach won't work. And the reason why is because as we're doing the sweep, we need to know everything in advance. We need to know all the queries. In particular, like we need to know when will some requirement stop being effective. At what query will it no longer be effective? For D3, we don't know that because we have to answer the first query before we even know what the second query is. So we have no idea. So we're going to try something basically completely different. We're still going to sweep down in water level. But the idea here is now, I'm going to draw something that looks very different here. So again, we'll imagine land cells just kind of appearing out of nowhere. But here's the idea. We'll have this land cell. Another land cell might appear somewhere else. And then we'll say maybe a land cell appears between them. So when this happens, we're going to consider merging two things together. We're going to perform this merge first, and then we're going to perform this merge here. So now we have these two different merges. What you can imagine this to look like is, in a sense, it's kind of a binary tree. So we kind of have these three nodes here. And then we merge these two together. We'll have this imaginary node here. And then we merge these two together to create this. And this red one is kind of imaginary. So yeah, we now have these trees, and we can imagine adding more nodes. So maybe we have some other node over here, and then we add a node here. I guess these aren't very axis aligned, but that's fine. So when we do this, we'll add, I'm gonna become low on colors here, but I think you get the idea. We'll add, let's say these get merged together first. So we have these two get merged into this. And then perhaps this and this get merged into a blue. So we have some tree that looks like this, and this represents every time we do a merge, we create a new node, and the two children are our children that we connect together in the disjoint set. So we've got this really nice binary tree here. Okay, so what can we learn about this tree? Importantly, every node in this tree has some time range for which it's the root of the tree. So earlier, this red node, this was the root up until these two things appeared. So this had some time range. Maybe just one of these nodes was just there alone, so it was the root for some of its own time. So each of these have some time period for which it's the root. And this time period doesn't change. The time period is static because the thing that's changing between queries isn't how the water moves, because the heights are all fixed. It's the time that we need to have a robot there. Which means this binary tree is totally reusable. We just have to figure out how do we do something good with this binary tree efficiently. OK, so yeah, I guess how do we? So what happens when we have a robot query? Let's say we were told, OK, at some time, we need to have a robot here. Well, if this happens at this node, at some height, let's say it happens at this height here, we want to know what did this tree look like when we were given this constraint. And we can find what is the highest node. Like let's say it's given for this node here, which is represented by this node here. This is the black node corresponding to this. We want to say what's the highest ancestor of this node that still contains this time. In that case, it's this node here. You can imagine maybe this gets merged with other stuff later on, and this has more parents. But this is the one that's relevant at the time this query was asked. So we can figure this out using binary lifting. I'll have a link to that in the description of the tree basics video, which teaches you binary lifting if you're not familiar with it. But we can figure out, yeah, what is the node that would be responsible for this at the time this query was made. So now we have this node here. Basically, we're kind of like binary searching how far to go up, and we can do that quickly with just a single log factor. So we know, yeah, what the component that's represented by this component here was in the binary tree. And that tells us basically, for this node, we're going to need to have a robot here. That's like the requirement that we're given. Later on, we might remove this robot, but this is what it looks like now. This is kind of a bit of a silly example because it'll, well, I guess we'll use it for now here. So we know we need to have a robot here, and this is like the first requirement we're given. Maybe later on we're told, or maybe some other time we're told very early when the water level is very high, we need to have a robot here perhaps. So that would be here. Maybe we need a robot here. And then maybe when the water level is also really high, we need a robot here. So this would be just this one here. So we need a robot here, here, and here. What that means is there was some time when we have just like this node, we need a robot here, and we need a robot here. So clearly we're going to need 2 robots because these are the only pieces of land we have. Or I guess we would have something like this. Maybe it looks like this. So we have the red component, which is this component here. We need a robot for it. We have this other component, which is just this. We need a robot for this as well. But later on, we need a robot in this whole thing. That could be either of these 2 robots. Either of these robots can like stay on its component as the component expands. So all we're interested in, if we're interested in the number of final robots, is the robots that don't have any children robots. So this robot does have a children robot, so we don't have to pay for it. But we do have to pay for this, because this is kind of like a leaf of this interesting tree that we're left with. This is also kind of like a leaf, so we have to pay for both of these. And that's the solution idea. Now the question is, how do you implement this in an efficient way? Because you also, like the important part that's a little bit tricky is you also have to be able to support removals. So which nodes are like marked here is what gets changed, which nodes have an R on them. That gets changed per query, and we need to be able to support updates to that very quickly. So there are a whole bunch of ways we can handle this. One way is to do something like when we create a node, we can see if there are any children nodes that are interested or that cover us. And we can do that using some sort of LR, like Euler prefix sum. But that's not entirely necessary. Perhaps an easier way is every time we add a node, or every time we mark a node, we're going to add 1 to the path from it to the root. And that means like, okay, we cover all of these nodes here. And then same thing for this node, we're going to cover all of these nodes as well. So this node is currently covered twice, which means not only is it unnecessary, but it's unnecessary because of 2 other robots. So we really don't need to buy a robot here. However, if we were to remove both of these, it might become necessary. So we have to handle that. So yeah, one way of doing this is with HLD. We can do heavy light decomposition. And the idea behind that is we can take the biggest path, the heaviest path, where a path is heavy if it is the child with the largest subtree size. And if you do that, then the path from any node to the root will take at most log n heavy paths. So we can decompose this into some heavy paths, and then we can do these updates. Every time we have a robot, we want to update the path to the root. And then when we delete a robot, we want to see how many, we're going to subtract 1 along this path, how many zeros did we create. Alternatively, you can save a log factor. This will be log squared per query. You can save a log factor if you use either link cut trees or splay trees. In other words, if you use splay trees the same way you would if you were using a link cut tree. And I won't talk about that here because this is a very complicated algorithm, way more difficult than what we've talked about so far in this problem. So if you're interested in link cut trees, I think Eric Demain has a great video on MIT OpenCourseware, which you can watch that explains generally how they work. But again, that's not necessary for solving the problem. It's only if you really want to optimize your runtime to have just a single log per query. Awesome. So that's the solution idea to problem D. There are 3 parts of it, of possibly increasing order and difficulty. Let me know if you thought D2 was actually easier than D3. It turns out interestingly, we had a solution to D3. One of the problem writers had a solution to D3 before we independently discovered D2 also exists. So there's also like an offline solution as well as the online solution. So yeah, let me know if you thought D2 was interesting as well, or if D3 is just the easier solution than seeing D2 anyway. Okay, hopefully you enjoyed, and hopefully you enjoyed the contest. If you were part of the top 25, we'll see you in Hacker Cup World Finals. Otherwise, hope you enjoyed the run, and we'll see you next year in the qualification round. All right, have a good day. Bye.